There is a ship sitting in a port in southern China that looks like any other research vessel. It has a tall drilling tower in the center of its deck. You could mistake it for an oil rig that lost its way. But this ship is built to drill a hole almost 7 miles straight down through the floor of the Pacific Ocean, deeper than any nation has ever reliably reached. And before it ever lowered its first drill into the water, scientists had already found something underneath that should not be there. You're watching Mistral Geo, and this is the story of what is hiding beneath the Pacific Ocean, and why China built a machine to go and find it. This is the Meng Xiang, China's first domestically designed and built deep ocean drilling vessel, and it was officially commissioned in the southern city of Guangzhou on November 17, 2024. Now, the problem with most ships is that they are built to move across water. The Meng Xiang is built to drill through the floor of it, and not just a little. It is designed to lower a drill pipe almost 7 miles beneath the surface of the ocean, about 11 kilometers down into the rock of the Earth itself. The actual size of this vessel is 179.8 meters. It is around 42,600 tons, which makes it the largest scientific research vessel China has ever built. And it can hold 180 people on board for the entire mission. For a more relatable sense of scale, if a normal research ship were the size of a small apartment building, the Meng Xiang would be closer to a floating city block with a 907-ton drill at the center of it. That drill is the heart of the entire mission. It's the world's first hydraulic lifting rig that can do 2 completely different jobs at the same time: oil and gas exploration on one hand, and pure scientific core sampling on the other. The same machine, 2 purposes. The Meng Xiang first mission was scheduled for the end of 2024. Its planned drilling operations in the South China Sea were laid out to continue all the way to 2035. The reason the Meng Xiang represents such a leap is not just its drilling depth. It's that the ship combines, for the first time in any single vessel, 3 things that used to require entirely separate platforms: deep ocean scientific drilling, oil and gas exploration, and natural gas hydrate investigation and trial extraction. Before this, those tasks were divided between different industries, different ships, different missions. The Meng Xiang merges them. One platform, capable of going wherever the science requires. With its commissioning, China joined a small group of nations alongside the United States, Japan, and Europe capable of independently conducting deep-sea expeditions of this scale. Tuo Shouting, director of the IODP China office, expressed hope that the vessel would contribute greatly to international research. Lin Boqiang, director of the China Center for Energy Economics Research, noted that advanced technology of this kind reduces exploration costs, enabling deeper exploration than ever before possible. In late November of 2024, an international workshop was convened in Guangzhou. Over 140 scientists from 8 countries attended. The workshop produced 3 formal recommendations. First, form a management committee and a scientific committee to oversee the effective use of the drilling vessel. Second, develop a funding model for its long-term operation. Third, carefully discuss where, exactly, on the planet to drill in order to penetrate intact ocean crust and reach through the Moho into the mantle. Because you only get one first attempt at touching the inside of your own planet. In November of 2020, scientists from China and the United States published a study that would quietly rewrite a chapter of geology. They had spent years installing a network of seismic stations across northeastern China, eventually more than 300 of them. The work began in 2009, originally with about 140 stations. Then the Chinese Academy of Sciences added more, building it out into one of the densest seismic arrays anywhere on Earth. The point of all of this was to listen. Seismometers don't just measure earthquakes. They measure how the energy from earthquakes travels through the earth, and because seismic waves speed up in some kinds of rock and slow down in others, you can use them to build images of what's underneath. It works almost the same way a doctor uses ultrasound to see inside a patient. Only here, the patient is the planet, and the ultrasound has to travel for hundreds of miles through solid stone. The team gathered more than 67,000 measurements from 313 regional seismic stations. What the team imaged is the part that doesn't make sense at first. They saw an old piece of the Pacific Ocean, the actual rocky slab that used to line the bottom of it, buried more than 400 miles beneath. Northeastern China. The slab wasn't sitting still. It was being pulled downward. It was sinking through the inside of the Earth. This rocky slab is called a fragment of the oceanic lithosphere. The lithosphere is the outermost layer of the Earth's surface, composed of the crust and the solid uppermost parts of the upper mantle together. It's the rigid outer skin of the planet, but it isn't a single sheet. It's broken into multiple fragmented tectonic plates, all slowly moving and shifting around the surface, occasionally running into each other. When two of these plates collide, sometimes one of them gets forced underneath the other. That descending plate gets pushed deeper and deeper into the planet, and it keeps going. The process has a name. It's called subduction. It's the engine behind earthquakes, behind volcanic arcs, behind the formation of entire mountain chains. It's also, in a slow and grinding way, the process that recycles the surface of the Earth, pulling old crust back down into the mantle so new crust can form somewhere else. We've known about subduction for a long time. What we didn't know was how deep we could actually see it happening. Before this study, scientists had only been able to image subducting slabs down to roughly 200 kilometers, about 125 miles. That was the ceiling. Beyond that, the picture turned to noise. The Chinese-American team broke through that ceiling. They imaged the Pacific slab at depths between 410 and 660 kilometers, between 254 and 410 miles below the surface. That depth range has its own name. It's called the mantle transition zone. It is a region where the pressure inside the Earth becomes so intense that the minerals making up the mantle are forced into entirely different crystal structures. The same atoms, rearranged. Like how liquid water and solid ice are made of the exact same molecules but behave like completely different substances. In the mantle transition zone, the pressure-induced phase changes happen at very specific temperatures and pressures. Because those parameters are well known, geoscientists can use the transition zone like a thermometer, measuring the temperature inside the planet just by looking at where the phase changes occur. The team identified two seismic anomalies, places where the waves changed speed sharply. They are called seismic velocity discontinuities. One of these discontinuities was the upper boundary of the sinking slab. The other was the lower boundary. For the first time, scientists were looking at both the top and the bottom of a subducted ocean floor at the same time, hundreds of miles down. According to Chi-Fu Chen, based on detailed seismological analyses, the upper discontinuity was interpreted to be the Moho discontinuity of the subducted slab itself. In other words, the same crust-to-mantle boundary that surface scientists are trying so hard to drill through was sitting there, hundreds of miles deep, pulled into the Earth along with the rest of the slab. The lower discontinuity, Chen said, was likely caused by partial melting of the asthenosphere beneath the slab, under hydrous conditions, in the seaward portion of the slab. Translation there was melt down there, beneath the descending plate, and the most likely reason for that melt was water. The slab itself was angled at a relatively shallow 25 degrees, sloping downward. The actual point where the Pacific Plate begins this descent is far to the east, near the Japan Trench. By the time the slab passes under Japan itself, it's already reached depths of around 100 kilometers. Northeastern China sits about 1,000 kilometers further inland from that trench, which is exactly why it offers such a good vantage point to see what happens next. According to New, the fact that both the top and bottom of the slab were visible in the seismic data was important on its own. It meant the slab hadn't completely mixed with the surrounding mantle. It had retained its shape. Even at depths where pressure and heat should have softened and deformed it dramatically, it was still recognizable as a discrete object, but it had also clearly changed. A lot of studies, New said, suggest that the slab actually deforms a lot in the mantle transition zone, that it becomes soft, that it's easily deformed. How much it deforms or retains its shape matters because it affects whether and how it mixes with the mantle and what kind of cooling effect it has on the deep earth as a whole. And that cooling effect is part of a much bigger picture. The earth's mantle convects, like heat in an oven. Heat from the core rises through the mantle at the center of oceans, where new tectonic plates form along mid-ocean ridges. From there, the heat flows outward through the mantle, cooling as it moves toward the continents, where it sinks back down toward the core to collect more heat, rise again, and complete the convective circle. This is the engine that drives plate tectonics, the engine that has shaped the surface of our planet for billions of years. A subducting slab is part of that engine. It's the cooled, dense return path for material that originally rose somewhere else. Understanding what happens to that slab at depth, how it deforms, how it mixes, what it carries with it is fundamental to understanding the entire system. And what happens next is where the real problem begins. When an oceanic plate gets pulled into the earth, it doesn't go down empty. It carries water with it, a lot of water. The sediments on top of it are saturated. The crust itself contains hydrated minerals that have water bound up inside their crystal structures. The very upper layer of the mantle, locked into the bottom of the slab, has water bound up inside its structure as well. As that slab descends and heats up, it begins to release that water. The fluids escape upward into the surrounding mantle, triggering a process called arc melting that eventually feeds the volcanoes you see at the surface. This is exactly how volcanic arcs like Japan get built. There's a lot of water in the slab descending beneath Japan, New noted, and it produces a lot of partial melt. That melt rises up and creates the arc volcanoes. That's how Japan was built. That part scientists understood. But here's the weird part. They didn't think the water made it much further than that. The conventional assumption was that almost all of it got squeezed out and released as the slab passed through the upper mantle. After that, the slab would be more or less dry. The deep mantle, by this logic, should be a relatively water-poor place. The new imaging suggests the conventional assumption is wrong. The team found heat signatures of partially melted material underneath the slab material that, by all rights, shouldn't be melting at those temperatures and pressures unless something was lowering its melting point. And the simplest explanation for what would lower it is water, which means the slab transported some of its water all the way down into the transition zone, hundreds of miles deep, far below where anyone expected it to survive. There is increasing evidence, New said, that a portion of this water stays inside the plate to go much, much deeper. Whether it is totally released at upper depths is still an open question. The data is starting to suggest that the answer is no. That alone would be a strange enough discovery. But there is a second problem with it. Hot, partially melted material is buoyant. It wants to rise. If pockets of melt are forming below a sinking slab, you would expect them to push back upward, like air bubbles trapped under a sheet of ice. Yet somehow, the slab keeps going down. The problem, New explained, is explaining how these hot materials can be dropped into the deeper part of the mantle. It's still a question. Because they are hot, they are buoyant. That buoyancy should act like a life preserver, pushing upward on the underside of the sinking slab. Yet the slab is still descending. The researchers proposed a possible explanation. The slab, they suggested, might be developing holes, tears, gaps in its structure that allow the hot melt to escape upward through the slab itself, while the slab continues to sink. If you have a hole, Niu said, the melt will come out. That's why they think the slab can go deeper. And those holes might explain something else that has puzzled geologists for years, volcanoes that shouldn't exist where they exist. There is a volcano called Changbaishan on the border between China and North Korea. It sits roughly 1,000 kilometers away from the nearest plate boundary. By the standard rules of plate tectonics, there's no obvious reason for a volcano to form that far from a subduction zone. We don't really understand the mechanism of this kind of volcano, Niu admitted. But melt rising from holes in a sinking slab could be a possible explanation. So the picture begins to look something like this. An ancient piece of the Pacific Ocean is being pulled into the Earth at a 5-degree angle. As it descends, it's tearing. It's leaking water into the deep mantle, and it may be feeding volcanoes thousands of kilometers away from where it first started its descent. This is what's actually happening underneath China right now. Water, after all, is the most common volatile component inside the Earth. It moves, it changes things. It makes rocks softer, melt easier, behave differently. Subduction zones are crucial sections where water gets transported into the deep Earth. The process has been investigated extensively around the Pacific Ocean using seismological and magnetotelluric observations for decades. Yet the distribution of water in the overlying mantle and the evolution of water after the breaking off of the subducting slab remains poorly investigated even now. This is why the deep Earth keeps surprising us. Not because we lack the science, but because we still lack the data. A second study, published in 2023 in the journal Nature Communications, deepened the mystery in a different direction. This one focused on the South China Sea specifically, a region called the Southwest Subbasin, located in the Western Pacific. The South China Sea has a long and complicated geological history. Its seafloor began spreading apart around 32 million years ago in its eastern subbasin, then expanded westward, before that spreading finally stopped roughly 16 million years ago. The Southwest Subbasin had its own opening history, from about 23 to 16 million years ago. It has a distinctive V-shape. Its relatively short opening history made it an excellent place to study, because it preserved important information about continental rifting and basin evolution that older basins have long since erased. To study what was happening underneath it, a team of researchers conducted a passive seismic experiment between June and December of 2017 on board the research vessel Xi'an, 3 of the South China Sea Institute of Oceanography. They deployed 10 ocean bottom seismometers devices placed directly on the seafloor alongside 3 land-based stations. Between them, they listened to the deep Earth for 6 months. Ocean bottom seismometers are an unusual kind of instrument. Most seismic data comes from stations bolted to dry land, where they're easy to maintain and easy to read. But land-based stations can only see so much of the ocean floor's interior. To really resolve the structure beneath a basin, you have to put your sensors on the seafloor itself, which means dropping them off a ship, leaving them there for months, and hoping the equipment survives the pressure, the currents, and the occasional curious sea creature. The team selected seismograms from 91 earthquakes around the world, earthquakes with surface wave magnitudes greater than 4.5, occurring at distances between 20 and 150 degrees from the array. Each event was recorded over a window of 7,200 seconds or 2 hours. The vertical seismograms were downsampled, processed, filtered, and then run through a tomographic technique called the two-plane wave method to build up a 3-dimensional image of the upper mantle beneath the basin. What they found was a quiet anomaly hiding in the data. At a depth of about 35 kilometers below the seafloor, The mantle on the northern and southern sides of an old, fossil mid-ocean ridge looked the same. Normal. Identical. The way you would expect oceanic mantle to look, with a shear wave velocity of around 4.3 kilometers per second on both sides. But as the depth increased, a difference began to emerge between the two sides. By around 50 kilometers down, the southern side of the ridge was showing seismic waves moving roughly 3% slower than the northern side. A 3% reduction may not sound dramatic, but in seismology, at that depth, it's a major signal. The estimated uncertainty in the measurements was only about 1%, meaning the anomaly was 3 times larger than the noise floor. It was real. It was significant. And it meant that something about the rock down there was different from the rock just 100 kilometers to the north. The slow zone stretched 100 to 150 kilometers from north to south, and it sat at depths between 40 and 70 kilometers. At 70 kilometers down, the slowest measurement on the southern side was 4.07 kilometers per second. The northern side, at the same depth, was 4.13. The question was different how. The researchers worked through the possibilities one at a time, methodically. The first candidate was temperature. Hotter rock slows seismic waves down. But for temperature alone to explain the anomaly, the mantle in that region would have to be up to 300 degrees hotter than the surrounding area, which would have caused massive melting throughout the entire mantle column, and other measurements ruled that out. The crust in the northern half of the southwest sub-basin was actually thicker than in the south, which implies more magma activity historically on the north side, not the south. The heat flow at the surface was also higher on the northern side, not the southern. If anything, the southern side was the cooler one. Temperature couldn't be the answer. The next candidate was composition. Could the slow zone be explained by mixed-in fragments of recycled oceanic crust, what geologists call mid-ocean ridge basalt, or MORB? The team tested it carefully. The math didn't work. Below about 70 kilometers depth, basalt should phase transition into a denser rock called eclogite, which would actually speed seismic waves up, not slow them down. The opposite of what the data showed. Then they tested another type of contamination pieces of the lower continental crust that had been trapped in the mantle during ancient rifting events. That worked, partly. About 5% of lower continental crust matched the readings on the northern side, which was consistent with previous geochemical studies based on basalt samples collected at International Ocean Discovery Program sites in the area. But explaining the southern side with continental crust alone would have required around 20% contamination, which was unrealistically high, far more than any previous study had ever inferred from chemical analysis. That left water. Structurally bound water can affect how seismic waves move through rock by changing the way the minerals respond to stress. It's a subtle effect, but over kilometers of rock, it adds up. The team ran their models with various combinations of water and continental crust. The numbers converged on a specific answer. The slow zone beneath the southern southwest sub-basin most likely contains between 150 and 300 parts per million of water, mixed with somewhere between 5 and 10% of lower continental crust trapped in the mantle. That is a lot of water for a mantle that, by older models, should have been relatively dry. Generally, the water concentration at mid-ocean ridges rarely exceeds 100 to 500 parts per million. Previous estimates of the water content in the mantle source of Southeastern Asian basalts ranged between 84 and 360 parts per million. The southern southwest sub-basin sits at the high end of that range and in a place where, by the simple cooling model of ocean basins, it shouldn't. Where did it come from? The team's best explanation traces back to an even older ocean. Long before the South China Sea existed in its current form, there was an earlier sea in the region, what geologists now call the Proto-South China Sea. The plate beneath that ancient sea was subducted southward, slipping beneath what is now northern Borneo and the Nansha Block. After the spreading of the modern South China Sea stopped around 16 million years ago, segments of that older proto-South China Sea slab broke off and sank into the deep mantle. Meanwhile, the larger Sunda plate above it continued moving, drifting about 500 kilometers to the southeast over those millions of years, at a rate of around 32 millimeters per year. The result is that the broken slab segments, which started in one place, now sit beneath a different one, specifically beneath the southwest sub-basin. And as they slowly fell through the mantle, they leaked water into the surrounding rock. Enough water to leave a trace that ocean-bottom seismometers, almost 16 million years later, could still detect. There were three independent lines of evidence supporting this explanation. First, shear wave splitting models showed that the direction of deep mantle flow beneath the Sunda plate runs from northwest to southeast. Second, the absolute motion of the Sunda plate itself is southeastward, at that 3-2 millimeter per year rate. Third, earlier geophysical and geological studies had already suggested the existence of post-subducted proto-South China Sea slab segments beneath northern Borneo. Receiver function analysis of the mantle transition zone beneath Borneo and the southern South China Sea had even revealed evidence of significant water leaking from that very slab. Earlier studies had proposed alternative explanations. One was that the water came from a deep mantle plume known as the Hainan plume, a column of hot material rising from much deeper in the earth. But if the Hainan plume were the source, the water would be distributed roughly evenly across the basin. It's not. Only the southern side shows the anomaly. The plume hypothesis doesn't fit. The slab dehydration hypothesis does. The deep earth, in other words, has memory. It remembers oceans that no longer exist. If there is one image that captures how strange the inside of the Pacific really is, it might be this one. A subduction zone, once it starts, behaves almost like a runaway train. As geologist Brandon Schuck of Louisiana State University has described it, getting a subduction zone started is like trying to push a train uphill. It takes a huge effort. But once it's moving, it's like the train is racing downhill. Impossible to stop. And ending it requires something dramatic, basically a train wreck. In November of 2025, a study published in Science Advances suggested that one of those train wrecks is happening right now. The Cascadia subduction zone is a particularly complicated one. It sits in the northern Pacific Ocean, off the coast of Vancouver Island. 4 tectonic plates meet there: the Explorer Plate, the Juan de Fuca Plate, the Pacific Plate, and the North American Plate. The first two are actively sliding beneath the third. It is one of the most geologically fraught corners of the planet and the source of some of the largest potential earthquakes in North American history. Earth's crust isn't one huge piece. It's multiple giant slabs of rock floating on a slowly moving, semi-molten mantle. The only thing preventing these slabs from drifting freely is that they are tightly locked together. Even so, movement does take place. The plates rub against each other, pull apart, and, in some places, dip an edge beneath an adjacent neighbor. When that dipping happens, you have a subduction zone. Schuck and his colleagues used a combination of seismic imaging bouncing sound waves off the seafloor from a boat-borne experiment and tracking the acoustic waves from earthquakes traveling through the earth to look at the structure of the northern end of the Cascadia zone. The technique works like a planet-scale ultrasound. Sound goes in, echoes come back. From the timing and pattern of those echoes, you can build a picture of what's underneath. What they found, beneath the seafloor, were multiple large faults and fractures. The tectonic plate down there is snapping under stress. The largest of these features is a fault about 75 kilometers long, roughly 47 miles, that is actively breaking the Explorer Plate. The pieces have not fully separated yet, but they are close. This is the first time, Schuck explained, that anyone has had a clear picture of a subduction zone caught in the act of dying. And the way it is dying is not all at once. The plate is ripping apart piece by piece, creating smaller microplates and new boundaries as it goes. Instead of a sudden collapse, it looks more like a train slowly derailing one car at a time. The evidence for this lies in where the seismic activity is happening. Some parts of the plate are no longer seismically active. Those are the pieces that have already broken off, no longer connected to the main descending system. Other parts are still tearing. Eventually, Schuck noted, enough material will have broken off that the subducting plate will slowly cease its downward fall simply because it has less weight pulling it under. It's a progressive breakdown, one episode at a time. And the geologic record matches it. Volcanic rocks in the area get younger or older in a sequence that reflects this step-by-step tearing. The story written in the fault lines is the same story written in the lava flows. So even the great machinery of subduction, which looks so unstoppable from the outside, has an end. And we are watching one of those ends in real time. There is one more piece to add to this picture. Studies of the mantle transition zone beneath the Japan Sea and the surrounding region have revealed an east-southeast, west-northwest elongated zone of significant thinning, extending from central Honshu in Japan all the way to the Korean peninsula. The thinning of the mantle transition zone in this corridor is striking, and it provides additional supporting evidence for the existence and distribution of a large-scale tear in the northwestern Pacific slab. In other words, the same Pacific plate whose old, deep fragment shows up beneath northeastern China appears to be torn open elsewhere as well. There is a slab tear under Japan. Hot mantle material from the oceanward side of the slab may be flowing through that tear and contributing to volcanism at the surface. To the south of the slab tear, the mantle transition zone is observed to be substantially thicker than normal. This suggests the existence of slab stagnation material from the descending plate piling up against the bottom of the transition zone, possibly because of strong resistance there that prevents it from sinking deeper. The methodology behind this finding is itself impressive. The data was processed using a 4-pole, 2-pass bandpass Bessel filter. After signal-to-noise filtering, more than 139,000 receiver functions from nearly 9,900 events were used in the final analysis. The receiver functions were stacked in 1-degree circular bins across the region, generating depth profiles of the mantle transition zone discontinuities, the so-called 410 kilometer and 660 kilometer boundaries that mark the top and bottom of the zone. Bootstrap resampling was used to estimate the uncertainty. What the team found, after all of that processing, was a clear pattern: a torn slab, a zone of stagnation, a planet whose interior is far more dynamic and far more broken than the simple textbook diagrams suggest. This is the same Pacific Ocean that the Meng Xiang sails on. Above its torn, sinking, dehydrating slabs, above the trapped water of vanished seas, above subduction zones that have been running for tens of millions of years and are now, somewhere, finally beginning to die. So put it all together. There is an old slab of the Pacific Ocean buried 400 miles below China, sinking through the mantle transition zone, possibly torn open by holes that allow molten rock to escape upward and feed volcanoes 1,000 kilometers away from any plate boundary. There is water, hundreds of parts per million of it, trapped in the upper mantle, beneath the South China Sea, leaked there by an ocean plate that broke off and disappeared 16 million years ago. An ocean that no longer exists in any form except as a chemical fingerprint deep inside the Earth. There is a major slab tear running east to west beneath Japan and Korea, with hot material rising through the gap and material piling up below it. There is a subduction zone in the northern Pacific that is currently in the process of breaking itself apart, tearing into microplates piece by piece, an entire geological engine slowly grinding to a halt in real time. And on the surface, parked in Guangzhou, and now slowly working its way into the South China Sea, there is a vessel called the Meng Xiang, designed to drill almost 7 miles down through the seafloor and, eventually, perhaps, through the boundary of the Moho itself, the boundary that has resisted every previous attempt for nearly 60 years. When we say that everything you were taught in school about the inside of the Earth is incomplete, this is what we mean. The textbook version is simple: a solid crust, a flowing mantle, a molten core, neat layers, like a cross-section of an apple. The real version is something else. The crust is not a smooth shell, it is a shifting, tearing, fracturing surface made of plates that occasionally rip themselves apart from the inside. The mantle is not a uniform layer, it contains buried fragments of ancient oceans, pockets of trapped water from seas that no longer exist, and regions where seismic waves move at different speeds because the rock is hiding things we are only now learning to see. The boundary between layers may not even be a single, clean line. The Moho, that long-sought doorway between crust and mantle, may turn out to be more of a transition than a wall, a fuzzy region rather than a hard edge, where one kind of Earth gradually becomes another. We don't know yet. We've never been there. That's why the Meng Xiang exists. After 2 rounds of sea trials, its key performance indicators reportedly exceeded design expectations. Its design met Super Typhoon safety standards. It can carry 180 people for 120 days at sea, traverse 15,000 nautical miles between refuelings, and lower nearly 1,000 tons of drill string into the ocean floor at depths approaching 11 kilometers. Its onboard laboratories are ready. Its automated core sample storage system is ready. Its drilling rig is ready. In late November of 2024, in Guangzhou, more than 140 scientists from 8 countries gathered for an international workshop dedicated entirely to one question: how to use this vessel to finally drill through the ocean crust and into the mantle. The workshop was co-organized by the Laoshan Laboratory, the China Geological Survey, and the National Natural Science Foundation of China. It produced 3 formal recommendations: form a management committee, develop a funding model, and carefully decide where, exactly, on Earth to attempt the drill. The co-organizers also encouraged collaborations with the wider international community to start new studies, launch new projects, and continue working with previously approved drilling proposals from other vessels. The era of single-nation deep-sea expeditions is, in many ways, already past. The questions are too big, the data is too valuable, and the planet is too interconnected. But the leadership opportunity, the international workshop concluded, is unprecedented. China is now positioned to take the lead in a new phase of international scientific ocean drilling, the phase that finally fulfills the 60-year-old quest of drilling through intact ocean crust into the mantle. Preparations for that future are currently underway, because you only get one first attempt at touching the inside of your own planet. And the next few years will determine whether the Meng Xiang succeeds where every previous attempt has failed. For all that we've learned, we still don't really know how the inside of the Earth works. We know that ancient oceans get pulled down into it. We know that water travels with them. We know that some of that water stays trapped for millions of years, recorded in the way seismic waves slow down through certain regions of the deep mantle. We know that the slabs sometimes tear, that subduction zones eventually die, that the layers of our planet are not as cleanly separated as we once believed. We know that an old piece of the Pacific seabed is currently sinking 400 miles below China, deformed and probably leaking, possibly responsible for volcanoes 1,000 kilometers from where any volcano should be. We know that beneath the South China Sea, the ghost of a vanished ocean is still releasing water into the rock 16 million years after that ocean stopped existing. We know that off the coast of Vancouver Island, in Cascadia, a subduction zone is dying in slow motion, breaking apart fault by fault. And we know that, For the first time in 60 years, there is finally a machine built to go and look. A ship called Dream, pointed straight down, aimed at a doorway no human has ever opened. The deep ocean awaits. The deep earth waits beneath it. And somewhere down there, in the dark, beneath miles of rock and water and pressure, the past of our planet is still moving, still leaking, still sinking, still tearing itself apart, quietly, over millions of years, in a slow and patient kind of geology that we are only just beginning to hear. What the Meng Xiang finds in the years ahead may confirm what we already suspect, or it may overturn it entirely. Some researchers believe the Moho boundary will look one way, others argue it will look another. What if neither turns out to be right? What if the inside of the planet, when we finally reach it, turns out to be stranger than any of the existing models predict? That has happened before. Almost every time we've looked closely at something, the answer has been weirder than the question. For now, all we can do is listen, and drill, and watch the data come back up the pipe. The more we study the inside of the Earth, the stranger it becomes. And every answer, so far, has only led to another question. That's how science moves forward.